Have you ever really stopped to wonder how we can predict the exact path of a planet or even just a simple curveball? It's not magic, not at all, it's physics. And today we're going to unpack the exact tools that let us describe every single curved complex path in the entire universe.
Just think about it for a sec. A football arcing towards the goal. A bird soaring through the air. Heck, our own planet orbiting the sun. The universe is absolutely filled with motion. But you know what? Almost none of it is a simple straight line. It's all about the curves, the twists, and the turns.
So that's the big question, right? How in the world do we precisely describe something as wild as a jet twisting and turning through the sky? I mean, the path looks completely chaotic, but the answer, well, it's surprisingly elegant. It really all just comes down to having the right tools for the job.
So, let's go ahead and open up our physics toolkit. The very first tool we're going to need is for the most basic question of all. Before an object even moves, where is it? To pinpoint a location in space, we use this amazing thing called a vector. A position vector is, well, it's pretty much exactly what it sounds like. It's an arrow that points from some starting point we all agree on. We call it the origin, directly to an object's location. The key is, it's not just a set of coordinates, it's a direction and a distance, all wrapped up in one handy arrow. And here's where it gets really powerful. We build this arrow, this position vector, from its simplest parts. We just describe, okay, how far do you have to go along the x-axis, how far along the y-axis, and how far along the z-axis to get to your object. Each one of those directions is its own separate, independent piece of information.
Okay, so we can pinpoint a location. But what happens when that location changes? Well, that brings us to our next key idea, displacement. And listen, here's a super crucial distinction you've got to grasp. Displacement is not about the long, winding journey you took.
Right. The displacement vector is what they call the as the crow flies measurement. It's just one single arrow that points directly from where you started to where you finished. It could not care less about the scenic route you took. It only cares about the most direct, straight-line change in your position. Simple as that. And figuring it out is actually incredibly simple. All you do is find the position vector of where you ended up, and then you just subtract the position vector of where you began. The result of that is one clean arrow pointing from your start to your finish. And that, my friend, is your displacement. This satellite example really drives the point home. Okay, so imagine it's orbiting from the North Pole all the way down to a latitude of -45 degrees. The distance it travels is that long, beautiful, curved path along its orbit. But its displacement, that's the straight shot right through the Earth, a direct path of 12,509 kilometers. See that? Two totally different numbers describing the exact same movement.
All right, let's grab our next tool and see how this all builds together. We know where an object is, and we know its change in position. But how fast is it going? And crucially, in what direction at any given moment? This is where we need to talk about velocity.
The velocity vector is basically a snapshot. It tells you exactly how fast you're going and in what direction at one specific instant in time. And here's a really cool visual for you. The velocity vector is always, and I mean always, tangent to the object's path. It's pointing exactly where the object is heading at that very moment. Okay, let's make this real with an example. Now, I know this equation looks a little intimidating, but just think of it as a recipe for position. The I, J, and K hats are just stand-ins for the X, Y, and Z directions. You can plug in any time t, and this recipe tells you exactly where the particle is along each of those three directions. Now, we're going to use a little calculus tool called a derivative. Don't worry, we're not going through the math, but it lets us transform that position recipe into a recipe for velocity. So if we ask, what's the velocity at exactly 2 seconds? The math spits out this answer. It tells us the particle is moving 8 meters per second in the x direction, 3 in the y, and 5 in the z, all at that one single moment. And if we just want to know the particle's overall speed, the number you'd actually see on its speedometer, we just combine those different directional speeds, and that gives us 9.9 meters per second. Boom. That's the speed of our particle at that exact instant. See how we went from a complex path to a single precise number? So cool. All right, we have our tools, position, displacement, and velocity vectors. Now, it's time for the secret that ties this all together. This is the fundamental insight, the big idea that lets us solve all these complex problems. Seriously, think of this as your new physics superpower. And here it is. This is the secret sauce, the idea that changes everything. Motion in one direction is completely, totally independent of motion in a perpendicular direction.
What that means is that the horizontal part of a movement and the vertical part are like two separate movies playing at the same time, and they don't affect each other at all. This lets us break one really hard problem into two much simpler ones.
To make this super intuitive, just think about walking around a city laid out in a perfect grid. How many blocks you walk to the east depends only on your east-west movements, right? Your decision to walk north for a few blocks doesn't change your eastward progress one tiny bit. They're completely independent.
This classic experiment just shows this principle in the most amazing way, so watch this. We've got two baseballs. One is just going to be dropped straight down. At the exact same instant, the other one is thrown sideways. Now your intuition, your gut probably tells you the dropped one is going to hit the ground first, right? But just look. Look at their vertical positions at each moment. They are identical. They fall at the exact same rate. Gravity only cares about the up and down motion. It completely ignores the fact that one of them is also flying sideways. The two motions are truly, completely independent.
So, why did we just go through all of this? Why does breaking motion down into these vectors and independent pieces actually matter? Well, because this toolkit, it isn't just for some problem in a textbook, it literally powers the modern world.
I mean, this isn't just theory. This is the principle at the very heart of the GPS in your phone. It's how air traffic controllers guide thousands of planes safely through the sky every single day. It is the hidden code that makes the physics in your video games feel so incredibly real. From forecasting the weather to plotting the course of a Mars rover, this way of thinking is, quite literally, everywhere.
So that's really the big takeaway. The most complex, crazy-looking, curved path can be understood perfectly just by breaking it down into simple, independent, straight-line motions. It's an incredibly powerful way of thinking that makes complicated things simple. Which, leaves us with a final thought. If this works for motion, what other complex systems in our world can be understood by breaking them down into their simple, independent pieces?